Ever wondered how data is transmitted over the internet? It's not just about sending and receiving information. There's a lot more happening beneath the surface. At the heart of this complex process are network protocols, a set of rules and conventions that control how data is transmitted between different devices in the same network. These protocols are the unsung heroes of our digital world, ensuring efficient, reliable, and secure data communication. Their design involves grappling with various key issues to meet the requirements of modern communication systems. These issues range from addressing and routing to data integrity, flow control, congestion control, sequencing and data recovery, connection establishment and termination, security, quality of service, scalability, and more. Each of these elements plays a vital role in shaping the success of data transmission and overall network performance. So, let's delve deeper and explore the key issues in protocol design. The first step in data transmission is knowing where to send it. That's where addressing and routing come in. Picture a bustling city. Each building has a unique address and a network of roads to reach it. Similarly, each device on a network has a unique address, and the data sent over the network must follow a certain path to reach its correct destination. This is the essence of addressing and routing. Addressing involves creating unique identifiers, like IP addresses, for every device on the network. It's like assigning a unique postal code to each building in a city. Routing, on the other hand, is about charting the best course for data packets. It's the GPS of data transmission, constantly calculating the optimal path for each packet, while also adapting to changing network conditions. However, designing efficient routing and addressing protocols is a complex task. It involves challenges like scalability, efficiency, and adaptability. But when designed right, addressing and routing lay the foundation for data to reach its correct destination. In a perfect world, data would always arrive exactly as sent, but we don't live in a perfect world, do we? Data transmitted over networks can get corrupted due to noise, interference, and other errors. So what do? We ensure data integrity. This means we confirm that the data received is the same as the data sent without any alterations. This is where error detection and correction come into play. Methods like checksums and cyclic redundancy checks, or CRC, are employed to detect any anomalies. If an error is detected, we've got to fix it, right? That's where error correction steps in. It's like a superhero, swooping in to save the day, correcting errors and, if necessary, retransmitting data. These processes work tirelessly behind the scenes, often unnoticed, but they are crucial. Error detection and correction ensure that our data remains intact, despite the imperfections of the real world. Imagine a highway during rush hour. Without traffic rules and control, it would be chaos, wouldn't it? The same applies to data transmission. Flow control is like the speed limit, ensuring that the sender doesn't overwhelm the receiver by sending data faster than it can be processed. It's crucial in maintaining network stability and efficiency, helping to prevent packet loss that occurs when the receiver's buffer overflows. Now think about congestion. It's akin to a traffic jam, occurring when network nodes or links get overloaded with too much traffic. To manage this, protocols need to incorporate congestion control algorithms to prevent packet loss and ensure fair resource allocation among multiple users. Techniques used can include reducing the data transmission rate and managing the traffic load effectively. So much like traffic rules on a highway, flow and congestion control are the traffic rules of data transmission, maintaining order amidst the chaos. Ever received a text message out of order? Annoying, isn't it? Now imagine that happening with your data packets. In the world of network communication, data packets being shuffled around like a deck of cards isn't a rare occurrence. But thanks to sequencing, our systems can rearrange these packets correctly, like solving a complex jigsaw puzzle. Sequencing assigns a unique number to each data packet, creating a map for their order. But what if a packet goes missing, lost in the vast digital ocean? That's where recovery mechanisms come into play. They're like the Coast Guard of data transmission, rescuing lost packets and ensuring they reach their destination. These mechanisms maintain timers and acknowledge received packets. If a packet doesn't arrive within a set time, it's considered lost and promptly retransmitted. In this way, sequencing and recovery mechanisms ensure that our data is not just received, but received in the correct order and in its entirety. Establishing a connection, keeping it secure, and ensuring quality, these are the pillars of a good communication experience. How do we establish a connection? Well, the process begins with what we call a handshake. This is a set of back-and-forth communications between the sending and receiving devices. They use this handshake to agree on the rules of their conversation, like the language they'll speak, the volume they'll use, and how they'll take turns. Once they've agreed, the connection is established and data transmission can begin. But what happens when it's time to end the conversation? The connection needs to be terminated, and it's important to do this gracefully. This means ensuring all data has been sent and received, and then sending a clear signal that the connection is being closed. It's like saying a proper goodbye at the end of a chat, instead of just hanging up. Now let's talk about security. It's a critical aspect of network communication. Just like you wouldn't want anyone eavesdropping on your private conversations, you don't want unauthorized access to your data as it travels across the network. This is where encryption comes in. Encryption scrambles the data into a code that can only be understood if you have the correct key. It's like talking in a secret language that only you and your friend understand. Finally, we have quality of service, or QoS for short. This is all about managing network resources to provide the best possible performance. It's like a traffic controller at a busy intersection, ensuring that data packets don't crash into each other and that everyone gets where they need to go on time. QoS mechanisms prioritize certain types of data, like video streaming or voice calls, to ensure they're delivered without delay or interruption. From the moment a connection is established to the moment it's terminated, these mechanisms work tirelessly to provide a seamless communication experience. In an ever-evolving digital world, being able to adapt and grow is crucial. This is where scalability and compatibility come into play in protocol design. Scalability ensures that as the network expands in size and usage, the underlying protocol design can accommodate the growth without requiring significant changes. It involves careful considerations in addressing, routing efficiency, and resource management. On the other hand, compatibility is all about ensuring that different systems and devices can communicate effectively. It's about creating protocols that are versatile and can work across a myriad of platforms and technologies. This is essential because in our interconnected world, data often has to traverse numerous networks and devices before reaching its destination. So in essence, scalability is about future-proofing your networks, ensuring they are ready for growth and increased demand. Compatibility, meanwhile, is about ensuring seamless communication across diverse systems. Scalability and compatibility ensure that our networks can grow and evolve with us. So, as we can see, protocol design is a complex, multifaceted process. The dance of data transmission across networks is choreographed by the thoughtful design of network protocols. These protocols, like conductors of an orchestra, ensure each part of the network performs its role precisely, maintaining harmony and preventing chaos. Addressing and routing are the first steps in this dance. Just as every dancer needs their spot on the stage, every device on a network needs its unique address. And routing, like the choreography itself, guides the data packets along the most efficient path to their destination. Now, even the best of dancers can stumble. That's where data integrity and error handling come into play. These mechanisms detect any missteps in the form of corrupted data and ensure they're corrected, keeping the performance flawless. Flow control and congestion control are akin to the rhythm and pace of the dance. They ensure that the data doesn't overwhelm the network, maintaining stability and preventing packet loss. It's like making sure the dancers don't collide or trip over each other. Sequencing and data recovery, on the other hand, ensure that the dance sequences are performed in the right order. If a step is missed or a dancer is out of place, these mechanisms ensure they're back on track. Connection establishment, security, and quality of service are like the stage setup, the security, and the overall performance quality check. They ensure that the performance is secure, runs smoothly, and delivers an exceptional experience for the audience. Scalability and compatibility are like the ability to adapt the choreography for different stages and dancers. They ensure that the network can grow and accommodate new devices without disrupting the performance. In conclusion, every data packet sent over a network is like a dancer, guided by the artful design of network protocols. Each aspect of protocol design plays a crucial role in ensuring efficient, reliable, and secure data communication. Next time you send data over the internet, remember the intricate dance of protocol design that makes it possible.